Good morning, algebra. It's good to see you all. I hope you're having a great day so far. Might not be morning for you. It is for me right now. So this week we are looking at exponential growth and decay functions, all right? So our learning target is how can I use and interpret exponential growth and decay functions, especially in real-world problems, right? Especially in real-world problems. So you'll notice I've written out an equation here. Y equals A, parentheses 1 space r to the t. You'll notice it's written on here twice. I've tried to highlight everything. And then we're going to talk about the difference between a growth and a decay function. Okay, the difference between them. So A is in green. It's our initial amount. T is our time. I kind of highlighted him in orange. R is kind of in a dark blue. That's the rate of growth, but we write it as a decimal. So typically you'll see a rate of growth as a percent. This is most relevant for when you are getting a loan or when you are buying a car. Anytime you get a loan, anytime you do savings accounts, anything like that, it's always as a percent. But when we plug it in here, it needs to be in decimal form. All right, it has to be plugged in as a decimal. So you need to be able to convert your percents to a decimal. Remember, percent literally means out of 100. All right, it means out of 100. So if it helps you, it usually turns into a 0 point, and then you have moved that decimal place 2. So if it's 6%, move it 2. So just to remind you. You'll notice I've highlighted in yellow here kind of the blankness between the two. So an exponential growth, if it's growing, if something is growing, then we are adding our rate to 1. All right, we add it to 1. If it's growing, it's increasing, we add it, growth. Decay is losing, right? Decay is decreasing. So for a decay function, we would subtract our rate. And this could be, for example, things that decay over time would be like the integrity of a piece of like metal that's left outside, like a shovel or something like that, right? It's going to oxidize, it's going to rust, and it's not going to be useful. Things that tend to decay just naturally in value are cars. You buy a car, and as soon as you buy it, it starts losing value. Sometimes eventually it will increase in value. Like we have some, classic cars that are worth a lot more, but pretty much as soon as you buy a car, it decays. And even those cars, when they were initially bought, they decayed in value too. So rare old cars, collectible cars are kind of an exception to this. But the car that you might be looking at buying, your first car, it's going to have to do with this decay function for sure. Growth functions. Growth functions would be, like I said, savings accounts, the money that you owe on a credit card. Those are all growth functions. So you'll notice that this space right here could be plus if it's growth, or it could be minus if it's a decay. So we're going to look at just writing some of these down. All right, we know A is our initial amount. And I should say that this is really similar to exponential functions in general. AB to the x, right? It's just that now our B is this whole thing here. All right, it's either going to be a rate of growth or a rate of decay. So our factor of B has kind of turned into this whole 1 plus R or 1 minus R. And then instead of X, we have T, because T is how we denote time. We recognize that X can also represent time. It can represent other things too. So I hope you can see that this exponential is extremely similar. This growth or decay is extremely similar to A equals Y, Y equals A, B to the X. Dyslexia kicking in there. All right, I'm going to scoot this guy up. And then the first thing I want to do, because it helps my brain, is I'm just my growth for these ones and decay. Because then I know which equation to look at up above. So this one's a growth, Y equals A, 1 plus R to the T. Now we need to fill in the things that we just don't know right now. First, we need our A value. Well, A is our initial amount. That would be 150,000, right? 150,000. Ooh, another thing that tends to grow house values. Just thought of that. I have my brother's buying a house right now. The next thing we need on here is our growth rate, which is 8%. But remember, it needs to be as a decimal. So I need to convert that. So that would be 8 out of 100. Another way of writing that would be 0.08. So if I just take my 8%, there's a decimal right here, right? So I would just move it 2. So that's how it turned into the 0.08. And that is for R. Now T is just going to stay there, all right? Y and T, they just hang out until we start to graph them or until we start asking questions like, well, how much would this, I'm just going to say house, be worth in 10 years' time if it grows 8% each year? So we've got Y equals 150,000, 1 plus 0.08 to the T. That is our function. We've got our 150,000 for our initial amount. And for R, we've got our 0.08. There. House values in our area right now, by the way, are about like 12%-ish. Some areas are growing by 15 or more. So just so you are aware, this is actually very realistic. All right, our initial amount for this decay function. Well, decay would be Y equals a 1 minus R to the T. What's our rate? It's 15%. What is our initial amount? It's 2,500. So this would be like buying your first car, approximately. So I'm going to rewrite this as Y equals 2,500, 1 minus my 15%. If I move my decimal place over, that would be 0.15. So minus 0.15 to the T. Oops. That guy goes there. That guy goes there. And I can simplify this down too. So Y equals 2,500. If I do 1 minus 0.015, I end up with 0.85 to the T. Why that matters is you can see that this is less than 1. That means it must be a decay function. All right, so if your B value, so to speak, if your B value is less than 1, it's going to be a decay. And if I simplify this down, we can see that this would be 150,000 times 1.08 to the T. Now that might not seem like very much, but because it is greater than 1, this is going to be a growth function. All right, so that sometimes helps us. It sometimes helps us by just looking at what their decay factor and what their growth factor are. Or if we use that Y equals AB to the X, what their B value is overall. So I'm going to leave these two for you to try out and write down for yourself. All right, so take a minute and try that out. All right, so let's take a look at some more growth and decay functions. I rewrote our growth and our decay right here, and then this is just the general exponential form, right? So the inaugural annual music festival is 150,000. Inaugural. For those of you who are not sure what inaugural means, it's like initial. Or the very first would be another way of saying it. So that is 150,000. Hey, look at that. The attendance Y increases by 8% each year. So there is our rate, 8%. Write an exponential growth function that represents the attendance after T years. So we would have Y equals, well, first of all, we've got an 8%. Automatically convert that to the decimal, okay? Convert it to the decimal. So I can move this 2 over, so it should be 0.08. There we go. Because I move it 2 decimal places. So I'm starting with my initial value, which is 150,000, and then 1 plus 0.08 to the T, right? I just filled in my A and my R. How many people will attend the festival in the 5th year? Well, if COVID's not a thing, because we have to recognize that this year, the 5th year, so that means our time is equal to 5, right? Our time is equal to 5. So I want to plug in my 150,000, 1 plus 0.08 to the 5. Hey, look at that. We're going to have to use our exponential rules. Isn't that so great? If you are someone who looks at me and goes, oh man, that hurts my head, I have a solution for you. It's called a calculator. So we've got 15000. There we go. 1 plus 0.08 to the 5. All right, that's what I'm plugging in. So, and this says to round to the nearest thousandth. Remember, this is your tenths, hundredths, thousandths, 10,000ths. So that 5 is in the 10,000ths place. So we want to round to the nearest thousandths. Well, that's 3. 1, 2, 3. So that would be, oh, thousand, not thousandth. Whew. Careful reading. Okay, nearest thousand would be tens, hundreds, thousands. So 220,000, right? We don't need the 399. So 220,000. All right, next question here. A website has 500,000 members, dollar members in 2014. Okay, I think this is a typo. My bad. The number Y of members increases by 15% each year. Write an exponential growth function that represents the website membership T years after 2014. How many members will there be in 2020? Round your answer to the nearest, to the nearest 10,000. All right, so it doesn't say it on here, but we're starting in 2014, and it has 500,000 members, right? 500,000 members. So that is our initial amount. And then right here, we have a 15%. So 15% as a decimal, I would move it over. So it becomes 0.15. So for our exponential growth, we'd have Y equals 500,000. 1 plus 0.15 to the T. We want to know how many members there will be in 2020. Well, first of all, we have to figure out how long after 2014 that is. So 2020 minus 2014 gets us 6. So that would be 6 years. That means T is going to equal 6. So I've already got my equation here. So we have Y equals 0.15 to the 6. So I'm going to plug that in. And we said to round to the nearest 10,000th. All right, so that would be right here, right? Because that's ones, tens, hundreds, thousands, 10,000s, 100,000. So 670,000. I will try and color code these because I was not doing very well at that. All right, for our next section here, it says determine whether each table represents an exponential growth or exponential decay function. Exponential growth or exponential decay. Remember, exponential growth, it gets bigger. Exponential decay, it gets smaller, right? Growth is when we are gaining value, or it's gaining amounts or gaining members. Decay is when it is losing. So take a look at your initial value and then ask yourself what's happening. Am I growing or am I getting smaller? What am I multiplying by, right? What am I multiplying by? And some of these do not go up by ones. That is okay. Makes it harder to find our rate, but I'm not asking you to write the equation. I'm just asking you Is it a growth or is it a decay? All right, so for this table right here, hopefully you can see we're going from 270 to 90. We actually multiplied by a third. 90 to 30, again, a third. And then 30 to 10, again, a third. So we are multiplying by a fraction. Another way of saying that is dividing by 3. Dividing by 3, it's a decay function. We're getting smaller each time. For this one right here, we go from 5 to 10 to 20 to 40. Hopefully you can see that we're timesing by 2 each time. That's a growth function. Right, growth. Put a G there. I'll put a D here. All right, for this one, we add 7, add 7, add 7. Hint, hint, hint. This is not exponential. He. Tricked you out on that one, didn't I? And then for this one, we're going from 64 to 16 to 4 to 1. So this time we are dividing by 4 or multiplying by 1/4 each time. So it's getting smaller. It's decay. All right, the next thing we want to look at, we want to determine the rate of percent for growth or decay. Okay, the rate of percent. Now remember, all of our rates so far have had either a 1 plus or a 1 minus. So we always have our initial amount, which is this guy. I can just ignore him, right? And this is going to have our rate in it. So this will really be, and you have to rewrite it, f of t equals 0.2. It's going to be 1 in either plus or minus something to get 0.98. Well, if I think about it, if I have 1 minus 0.98, then I can see I've got a 2%. Now, would I have to add that to the 1 or subtract it to get the 0.98? I need to subtract. Right? So we have to rewrite. So I rewrite it, and I can see that my decimal here is the 0.02. Well, what is that as a percent? If I move it back, it would be 2% decay. How do I know it's decay? Because I have to subtract, right? That's how you know it's decay. I think the growth ones are easier to see personally, because here we know our initial amount is 5. And when I go to rewrite it, I get y equals 5. And then I have to ask myself, well, am I adding or subtracting to get to 1.07? I have to add, right? I have to. Because if you start with 1 to get to 1.07, I have to add 0.07 to the t. Well, what percent is that? If I move my decimal twice, I get 7%. And again, because it's got this plus here, this is a growth. All right, I'm going to let you take a minute to try these two out. Okay, take a minute, try these two out. So for this one, you should have gotten an 8% decay. All right, 8% decay was the answer. If you're interested in seeing the work, I encourage you to check out my answer key. And then for this one, you should have gotten a 20% growth. All right, 20% growth. These two are a little different, and I want to point them out because you actually need to use your exponential rules. Isn't that great? I know, you're super stoked. So we need to evaluate this when we have just t here, but we have a 10t. All right, we have a 10t, and that's a problem. Now, the nice thing is that I know that this is being 10 times t. Well, in order to multiply those together, I had to have had an exponent of an exponent, right? It would have been something like a to the b to the x. And then that would get me a to the bx. So I'm going to undo that. So to undo it, I'm going to turn it into 3 parentheses 1.02. I'm going to leave my t out here, and I'm going to move my 10 inside. All right? So it's going to be 1.02 to the 10th power, all of that raised to the t power. So when I do that, I get 1.21 2. Just going to help myself there. So this would be 3, 1.22 to the t. Why did I pick 2 decimals? Because it was 2 decimals here. Okay, just so you know, I wasn't being arbitrary. I was just keeping it with 2 decimals. You do that especially in science, right? You look at the significant figures, and that's how you round. So then I can see that this is greater than 1. That means it is a growth factor. And I need to ask myself by how much? Well, if I do 1 minus 0.22, 1 minus 1.22, you get 22 or 0.22% growth. So this one, same thing. I need to rewrite it. All right. So this one would be like if you had a to the m times a to the n, you would get a to the m n. And m plus n. Sorry, I'm very close to the edge. There we go. So that adding right there tells me that what I really had when I rewrite this was 0.95 to the t times 0.95 squared. Well, 0.95 squared is 0.9025. I've only got 2 decimal places though, so I'm just going with 0.90. Now, this would be the initial amount, and then the 0.095 would be my rate, because you'll notice that this exponent now is just a 1, right? It's not there. So this is my initial amount. This would be my growth or decay factor. If I look at that, it is less than 1. That means we are decaying. So if 1 is what we started with, and now I'm at 0.95, I had to subtract 0.05, and that would turn into a 5% decay. Okay. All right, I hope that this helps. Please email me if you have questions. We're going to look at compound interest, which is like banking, very specifically banking, in our next video.